road from us, and she will be giving this keynote lecture on the future of biomedical research here in Portugal. And then we have 3 oral presentations by David Pires, by José Pedro Gil, and by Idálio Viegas, followed by the pitch presentations of the master's and PhD students that have submitted their work and that are candidates to the award for this track. And so without, we are not in a hurry because of the number of students that have to present is fewer students than in other tracks, and to make everybody's presentation the same length of time, we had to shorten the presentations to fit the one with the largest number of participants, which means, in other words, that we are okay with time. So, but without further ado, I'm going to ask Maria to come to the stage and give her presentation. Maria, you have half an hour, okay? Maybe what we can do is we can ask questions immediately after each presentation, or we could leave it to the end. But since these are different topics, I think it's probably wiser if we have a few minutes of discussion after each presentation rather than leaving it until the end. And so now, please, sorry, Maria.
Do I change? Thank you. Okay, first of all, good morning to everyone. It's a pleasure for me to be here. I'm glad that we are not short in time, okay, and I'm sorry for this delay. Oh, totally my fault. I was convinced that I needed to be here at 2 for the thing, and somehow I got confused and I didn't realize. Yeah, I just realized, okay, no, so, okay, so what I decided to do here is I work on malaria, so I work on an infectious disease, but I decided not to present work that we do in malaria, but something that we have been developing now for 1 year, 1.5 years. In fact, I think the pandemic was the really trigger for what I'm going to present here now, and was something that is on my role, not in fact as a researcher in malaria itself, but as an executive director of Instituto de Medicina Molecular. So at the Instituto de Medicina Molecular, basically what we do is, all kinds of, is a very broad type of biomedical research institute. It's really, one of our founders was the medical school of the University of Lisbon. So it makes sense that, we study from molecules to humans, from, diseases to exactly how RNA molecule moves out of the nucleus, or why a nucleus of a cell is important for the function of the cell, to person like me, to people like me that works on a disease like malaria, but really because it became a long time ago, many decades, years ago, okay, let's not put it in a bad way, but many years ago became fascinated by an organism that is called Plasmodium, to people that work in cancer because they really want to find an immunotherapy to cancer. So really is extremely broad. But being broad is really a discovery research institute. With that, I mean that really people are driven by discovery. And the way that we recruit these people is really because we recruit them because we think they have good ideas and they have the energy to bring these ideas into action and to really make discoveries. And so is the discovery and the curiosity of the researchers that drive our type of research. And I'm going to tell you how, in fact, we thought now to be this, but with some addition, okay? So, and I thought this would be important in the global way of thinking of this conference, that is the future of health. So basically, what we have been thinking, and now for some time, in fact for several years, but I think the idea that I'm going to bring to you here is a more recent one as a solution for something that we have been thinking for several years. And this sentence takes a forest to grow a special tree, and basically what we are sometimes thinking, and really research think, is that why does it seem great for science? We just finished a pandemic. Was the key for us to be able to be in this room without being too much moving, right? It's really at the speed that even several decades before, and now was able to deliver. But still, it looks great. You have really people that, people are not believing in science, although we have more and more educated people. Part of this is in countries where you have a high that are country. And still, they don't think that, because you cannot, my voice is quiet, but it's because I like to move. Okay. So cannot be that high. They listen, they hear me from here, is what you mean? Okay, of course. Okay, so of course. Sorry about that. So it's really, we should be in a fantastic moment, and really it looks very great. You have people that really don't seem to believe in science, and more than that is society that really think, what are scientists doing there? There is really, yes, is a moment that they should have realized that was necessary 3 decades on RNA, or 3 or 4 decades on RNA discovery to then be able to deliver, vaccines in less than 2 years. But it's difficult to explain that, okay? And that is also because science requires a lot of funds initially for these several decades then to be able to deliver. So you need to, as a society, to put some money in a black box that you don't have any idea what is coming, will be coming out. And we cannot really promise more than, we are just being triggered by our curiosity, and we are driven by discoveries. But that should be what science does and should be like that. So in fact, if we really, go into the science, and I put here, if you look to a forest, what science does is the roots of this forest, okay? Is really, what is in the bottom that you don't see it so much. You don't look if you go now to go for a walk in a forest or something like that, or even if you feel like if you give someone a bouquet of flowers, okay, that flowers will last for only 2 days. If you give a vase, or if you give a plant, it will last for a long time. And science, discovery science, what we do is this kind of roots that allows for a long time. But the truth is that it's extremely expensive, okay, is really, the results don't come around very fast so that people can see. In fact, in the past, we had the tendency to really deliver results that are really long-term results, but with headlines that look like it's going to be short. And I think we did it wrong. So people really believe that would be so much shorter than indeed it is. And so all this creates a little bit, of a gray moment sometimes for science. And it's not from now. I think it's been for a long time. It's only that now it's really surprising. We just finished from a pandemic. We solve a lot of problems and still are there. On the other hand, if we really focus just on translation is like the bouquet of flowers, or is the top of this forest. It's really beautiful. It's really fantastic to see. It really have a solution at the moment, but really, if it does not being fed by the roots, it's going to be finished very soon. Okay, so it has a quick wins, but these quick wins, if they are not fed, they will disappear very quickly. Okay, so in fact, what we are proposing here is that to really grow a special tree in this type of forest, you need to have probably both. Okay, you need to have translation in a way that society sees that you really have solutions, and you need, also something that is very basic, that is really discovery, to feed really the solutions for the future, because nobody knows what is going to be a problem next year. We didn't know in 2019 that we were going to have this type of pandemic, okay? But you need to be prepared for it. And that is what is difficult. So you need the science discovery, science that does that. And wherever it's there in terms of knowledge, it will be used when you have a problem and you need to find a solution. And of course, we should never forget that any kind of solution that we could think, I think in any kind of field, but for health, as always, you can really pinpoint all this discovery, sometimes has done more than 100 years before or decades before, but you always can pinpoint that discovery moment that now is the reason for you to find a solution. So basically, what we think is that we need to have a little bit of all this, but when I said that it needs a full forest to have a special tree, of course, you don't need to have all these in one single institution, okay? I think what it needs is like, as we are thinking here, University of Lisbon should have all, should have institutions that are really very basic, driven by discovery, and institutions that will be, or individuals or researchers that will be more in terms of finding solutions for problems that we are now. And I think the university, as I always have defended, should be the center of our society and should have this type of answers, should be the entire forest, okay? But I'm going to give you now something that we have been thinking about our own institution, about Instituto de Ensino Molecular that I just mentioned to you before. And basically, the path that IMM has been doing has these 4 different type of axes, okay? Of course, what is the main axis that we need to concentrate very much is science, okay? This one in the y-axis in the left, and is science. Of course, discovery depends of how good is our science, how good are our scientists, how good they are and driven by their curiosity, and how good is the conditions that we have as direction to offer them to really produce the best science, okay? Of course, then we have also innovation. That was something that I should say that was not axis, that we thought for a long time, okay? Obviously, everything is new. Discovery by itself is new and is innovation. But the innovation, as we put it now, as something that needs to make a shorter term between the discovery and reaching whatever target it is something that was not in our DNA from the beginning. Innovation was just in our DNA that, yes, what we do is new. Okay, it's novel. People don't like the word novel, but it's true. Is we are explaining a part of the world that nobody has explained before. That should be the base of discovery research and is also innovation. But innovation, as is transmitted in our society now, is something that for our institute is something more recent. And then we have the dialogue. And dialogue, I mean, really talking to the society, not only because we understand that society is the one that really, support us. We are using money from taxpayers in a way or another. Of course, we also use from private foundations, etc. But even that is part of the society. And we need to explain the non-scientists why we do it and why it's important, okay? And we have on the bottom one, management is something that we realize that it became really, really important for us to do. For all the other axes, for innovation, for dialogue, for science, if we really have a structure that is organized, it really makes life of everyone much easier and even easier to explain to the world outside that is we are doing it in a professional way, that we have organized and really transmitting how innovation really can go faster. So we already had this axis, but as you can see, is I have these dark green boxes as we think we did for the last 5 years. And then suddenly we had the pandemic. So we moved forward a little bit in a direction that probably we were not expecting, but we moved. And what we really want to do it next and have a long-term vision is what I'm going to present here. So let's go into this axis, science. This is what we do. And this is just some examples of what we have published in the last few years, very short time period, okay? And Idali will present to you, for example, a beautiful discovery that he has made in the last few years, published quite recently, and is really a beautiful discovery, and this discovery for discovery. I think what he has discovered probably will have a huge impact, not only in a parasite as he's doing, but probably in cancer and this and that, and is why it was a Nature paper. But really, that was not the driver. The driver was just understanding something that was happening there, and nobody has explained before. He made an observation nobody had done, and he's saying what that this means for biology of this parasite. And this is beautiful, and this is what we do, okay? And then, wait, sorry, okay, wrong thing. Then we have here, and I go here exactly for, even in terms of science, of course, for Idalio to be able to do this, he needs to have a supervisor, a group leader that is able to attract funds. And that is what we count of our research. And this way also we evaluate them, is that we evaluate their curiosity, their way of taking that curiosity forward and make discoveries, but also the way that they have to fundraise and be able to attract funds for this. And of course, our scientists have been doing quite well. But then we have here innovation. And I told you that this one was a little bit more a kind of delay there, okay? And in terms of innovation, it's true. We have not really taken too much into attention, but we have been lucky in a certain aspect. Although I don't think there is luck, we have been lucky in a certain aspect. So the team of Bruno Silva Santos, with a PhD student, and Nathalie Idálio was a PhD student, Daniel Correia was also a PhD student, long before Idálio, but basically Daniel, some years ago in 2011, he made a discovery that one type of cells in our blood that belongs to a group that is called gamma delta T cells. Gamma delta T cells are already below 2% of our immune cells in circulation. A small proportion of these had a kind of a feature that was really tumor killing type of feature, was really a strong tumor killer, but was a very small percentage. So is why your immune system is not able to make anything when you have tumors with that, because it's a small percentage. But what Daniel found was a way of growing these cells in vitro in a very, very special way, and really multiplying by millions the very one each of these cells. And by doing this, basically they created a concept of immunotherapy, that if you have a cancer that could be a target of these cells, you take cells from you or from me, okay? They take the cells, they would grow in vitro, and then they would check again in millions of different ways. And this was something that they did, they patent, they published, they patent, they published, they patent again, different modifications, how to grow this. They made a cocktail on how to grow these cells, how to really, focus on a specific particular of these things. And they made a company. And with this company was called the attention of another company in UK that had the same type of technology, but not a so good result. And basically they merged initially, and they start to be a British company. But now, the last year and 2 years during the pandemic, the Takeda International really bought all this. And now this immunotherapy, this specific one that was developed by Daniel Correia, is really being tested in patients in the United States in phase 1 trial. Okay, and this was something that really we did without giving too much an environment. I think IMM always gave a good environment to researchers to do discovery research, but we really never did created any special conditions for them to make discovery researchers that they could take forward. Okay, so we thought, based on this, and especially because I was part of these negotiations, and I can tell you that the majority of the time I was almost doing bluff. I didn't know exactly what I was negotiating about. These people were so much more experienced than me. I didn't have any, which was not difficult. I was zero experienced, okay, but they were really experienced. I didn't know exactly what we were doing, and I thought, okay, we cannot do this anymore. We need to really have, people that know what they are doing, that they are professionals on. And with that, we created in 2018 for the first time a tech transfer office at IMM. And this is the result of, since 2018 until this was prepared, this slide 2 months ago. So it was until 2 months ago. And you can see that the numbers are incredible, okay? We have, and I think the ones on the right here, I think probably are the most interesting ones to see, is like we have 5 startups, okay, created, 2 spin-offs that were really, really created, 5 are really under construction. And these ones, this is not even funds for IMM, it's money for these companies, okay? They were able to recruit more than 75 million euros for these companies. Just for you to have an idea, last year's budget for the entire IMM with 34 research groups, etc., was under 20 million euros, okay? So we are talking about something that obviously science can do, and this was, all these startups are based on researchers that really did discovery research, and then they just had people, professionals that can do after that. And we were not able to do this before 2018 because obviously our selection is for discovery researchers. We want to continue to do that because they are the ones producing the knowledge, and they didn't have anyone to do the follow-up. And this is something that, is very interesting. But then COVID came, okay? So this was created in 2019. This was the way that we were going. And COVID came, and on 10th of March of 2020, I had a colleague, João Rico Fonseca, is a medical doctor at the University Hospital in front of our institute, okay, Hospital Santa Maria, that called me desperate because, the entire world was desperate. It was not only typical of Portugal, but the problem is that they had an hospital, already some positive patients there. And there was one particular patient that entered the hospital that was a chronic patient, this type of patients that spend some months per year in the hospital. They know the entire teams, they are seen by entire teams. And especially this one, according to what I heard from descriptions, is a very social person, okay, can walk out of the bed. So basically it was positive. Nobody knew that it was positive. It was not tested until the WHO changed the criteria and everyone was tested in the hospital, and then it was positive. Nobody knows if it came positive, if it became positive in the hospital, but it was positive. João da Fonseca has a team of more than 30 people. Every 30 members of this team remember to have contact in the previous 2-3 days with this patient, okay? Some of them in a very close contact because they are the doctors or the nurses that really deal with the patient, but other ones spoke to him. And so the problem is that they all wanted to be tested, but the hospital only had tests to test 4 of them, and out of 4 of them, 3 were positive. Okay, and of course everyone was a little bit in panic, but there were no tests. Only 2 companies in the world, QIAGEN and Roche, had international permission for PCR tests for COVID-19. So João called me, and basically I call 10 minutes later, a member of my team at that time, Vanessa, that is the first person there on the left, and I ask her, Vanessa, the hospital needs, I think it's a PCR test, must be, it's an infectious disease, must be a PCR test to do this. I think we can create this. I work on malaria. I work mainly on the liver stage of malaria infection. It's also a needle in the haystack. So you always use PCR almost daily, on a daily basis to detect the parasite in the liver. So we thought Vanessa was the one that always used this for, so we thought should not be difficult. And Vanessa said, of course it's not, Maria. I'm going to check this. 1 hour later, we were on the phone again, talking what WHO had, what CDC had in their sites. Of course, you know, primers were not there because this was covered by patents of these other 2 companies, all these type of things, but we could design several. The problem was, where are we going to get the buffers? Because obviously if we need also to import them, it's going to be a problem at this time. And then Vanessa had this idea. We have this company, this Portuguese company that sells us this type of, you know, kits already for the PCR of Plasmodium, of our parasite. But I'm sure that they have for virus and things like that. We could test all the combinations that they have and see which one would work better for here. So basically, in a few days, Vanessa called for volunteers at IMM. This was 10th of March. By 13th of March, our institute had to close because the entire country closed. But Vanessa called for, you know, the help of PhD students, group leaders, postdocs, everyone, you know, that could help in different ways. And basically we created a task force of a diagnostic, okay? And until 6th of June, we were with these volunteers, were more than 100 volunteers, and basically in collaboration with the Ministério do Trabalho e Solidariedade Social. So it's really the ministry of that has the homes for elderly people, that is responsible for homes of elderly people. We start together with 21 more research institutions in the country. We use a protocol that was based in our institute and basically was distributed all over. Then different labs start to even make modifications, use different reagents, but this was the way that all started here. And we were able to have this. But then, of course, why I say 6th of June, 6th of June, in 2020, our country opened again. The lockdown was not anymore. People could start to do their PhD projects, postdoc projects, etc. And of course, we want them. They are discovery researchers. They were there just as a volunteers, as you know, as workers, as a kind of a company. But obviously, they are discovery researchers. We don't want to continue. But the Prime Minister called me and our attention said, "We want you to continue to do this." And I said, "I cannot do this because we have done this with the volunteers, and we want these volunteers to go back to their projects." But then we had a private group, economical group in Portugal that funded us, and we created a laboratory with machines, with robots, etc. And we created one laboratory that only with 6 people had the capacity to do up to 3,000 tests, PCR tests daily. With the volunteers, we had the capacity, we reached 900 tests daily, although our capacity was designed for 600, okay, but they were fantastic and they did it, whatever was necessary. But later on, we really designed just with 6 people, but with machines, basically a laboratory that has this capacity, and we start to operate, okay? And later, you know, we had to also, is one thing that we had to learn. We need to change teams. You know, Vanessa was fantastic and the volunteers were fantastic for the discovery to implement that initially, and Vanessa was incredible, but then she felt that it was not her job anymore. And we had another person, Patricia Napoleon, that now really built something in a professional way, and we start to do this. And basically, even we created at one point, we rented cars, we employ nurses, we employ drivers. They were going to 5 different districts, 82 councils in the middle part of the country. And they left every day, 7:30 in the morning, and do this. But why I'm telling this story? Because this is an amazing win-win story. With this, only IMM saved to the government 14 million euros. If they have done this with any other private lab, and not us, because we made really what we thought it was a fair price for whatever we were having there, they would have spent more 14 million euros. But IMM itself, in the end of this operation, had made profit. We are a non-profit institution. Of course, we cannot, it's not profit in that way. We need to apply to research, okay, to money, but we made a kind of a profit of more than 5 million euros. And this is really a win-win solution and type of situation that we thought, can we reproduce it again in different ways? And so it created a concept that we now call IMM Care, okay? And basically this concept is based on our experience of COVID. Basically we need to think, and we need to create what kind of a mission. What are the missions? The COVID-19 was a mission. What kind of a mission would we have next? And we need to think about these missions. Then we need to assemble a research team that really can find a solution or a prototype that solves this mission. And in fact, after a mission, you can even have several research projects, because, you know, we can have several teams or the same team working different, what we call flagship projects, that will see what would be the best solution. And after that, we have a kind of a logistic team that will make the deliver. We really massify the prototype, the solution that we found to the target population, okay? Of course, this is really the IMM Care concept was created kind of a year ago, and now it's becoming, you know, going to evolve and became part of a proposal that we are putting together with Vall d'Hebron Research Institute in Barcelona to European Union, and is much more complex than that. We are not basing this on in Portugal, not only for missions that are in Portugal. We even have a program that I think is really, really cool that is called the Ignite program, if we have the money, of course, but if we have the money to have an Ignite program, that will be, we have missions and our problems that are from the world, but the solution might not be the best one here. So we open calls that, like, based on the experience that the Gates Foundation had with the Challenge program, we open call to the entire world and say, we have a mission here. Does anyone in the world out there has a good solution? And so people will apply and the best solutions will win money. And then they start to work with our research teams to really, you know, make sure that we find the best solution, and because we know that science is like that, is with communication with the entire world. And we have many other things that obviously are part of this. And of course, this is always, I think, with a concept that is really, and is a kind of aspect that as humanity, we have decided long time ago, decades ago. And basically, when we signed at the city of Alma in Kazakhstan with the United Nations, more than 140 countries signed the Alma, what is called, is Alma, now I found, Alma-Ata, exactly. The Alma, thank you very much. Alma-Ata, okay, is really this concept, is the concept that health is for all. And our concept here of IMM Care is this, is that we'll find solutions that are at a fair price, that are able to reach everyone, okay? So it's not for free, is not, because it has a price. Science and research has a price, but this is something that we can make much more at a fair price and really distribute to the target population in a fair cost, okay? And that would be that we will then be able to distribute by everyone that is in need of that type of solution. Our action scope or focus areas are divided in 3 aspects mainly. One is the mission labs, and what we call mission labs is just, in fact, our laboratory that was created by, as I told you, in the summer of 2020 for the molecular diagnostic of COVID. Now we are reformulating this and will be the responsible is a team that, now can work on a problem. 6 months later can be working on a different problem. It's a different type of research that we have at IMM, that they are just driven by their curiosity. Here they are not driven by curiosity, they are just, driven by the mission and the solutions that they need to find to these missions, okay? Then we have what we are calling 2 other platforms. One is a clinical trials platform, and we are trying to really teaming with Hospital Santa Maria, and we could be like a way of speeding up some clinical trials, some solutions, again, always with the same principle. Science is close to it. We can speed up these. We can really find better solutions quickly at a fair price, etc., or fair cost. And then a biobank that we already have at IMM, as part of the Centro Académico Médico de Lisboa. In fact, IMM Care is really in this spirit of what we call the Academic Center of Biomedical Research in Lisbon, okay, that contains not only IMM, but also Hospital Santa Maria and the Medical School, Faculdade de Medicina da Universidade de Lisboa. And this biobank will be a next generation. What we want is to create something here that you remember that I had an axis that is dialogue, and we want the population to be part of this biobank. Imagine that you are turning 16, you are already allowed to give samples to a biobank, okay? And this is a present that your parents would give. It's like, why don't you, your parents will introduce you to this concept, and you are on of your own samples through blockchain. You can really, every time that you go a blood test or go to a doctor or something like that, you have a kind of a plate, of course it will be digital, doesn't need to be in your neck anymore, okay? But it's say I'm part of this biobank, so I want to give a sample. And imagine, of course, at 16, you are expected to be very healthy, okay? But throughout lives, you will have health problems, or hopefully not, okay? But you would be part of this, and you will construct collections like that, and very specific collections in a longitudinal way. So it's a kind of a dream. Obviously, this is is something that we are planning, and is a long-term project here. So basically, I just brought here this concept that really takes a forest, but sometimes even in the same institution, the forest, each tree could be all the different researchers, and are very different types of research that makes a very special tree that we hope that at IMM one day would have these 2 kind of, aspects of biomedical research. And thank you very much.
Thank you very much, Maria. Very interesting and and a big challenge as well, obviously. And I would like to ask if there's anyone who would like to ask questions to Maria about this exciting project. Anyone? Yes? Oh, so many. That's great. Okay, so.
Thank you. Thank you for your presentation. My question is regarding the IMM Care initiative. So this is a really promising and interesting mission. In your experience, what are the main difficulties that institutions find when trying to implement these kinds of projects?
We are just starting. So I'm still in the honeymoon phase, so I don't think we are going to have any problems, okay? So I don't know. No, of course, the main problems that we would face in a structure like that is we would have several aspects that probably can fail. One is that first, it will be our naivety. one problem that we need to avoid is that we are so naive that we think everything is going to be a solution and is not, okay? I remember that when we were writing this proposal, we were thinking about 12 different missions to start in the next 6 years. We are not designing already this, let me go there, because if not, Miguel, you are in the front, sorry. If not, so basically we propose that we will start 12 different missions, okay? And in my thing is that, of course, we didn't name these missions because we don't know them yet. We are going to create what we call a brain trust of people from Portugal and outside of Portugal that will design what would be the missions, so that they will put us the missions. But we just designed 3 as an example, okay? And then at one point I thought, okay, all successful, something like that. And the person that was helping writing, in fact, was the main person writing the proposal, was telling me, Maria, obviously, if you have 40% that are successful, that is already a huge success. So one, I think that we'll face is from our side, our naivety on starting something like that. On the other aspect, of course, all the structures, imagine that, all this is very interesting to say that is a fair price and everything, but we could see that, we could feel already that, for example, even during the COVID-19 thing, and we are in a war, so it's even more easy to explain, but we had some type of forces that were against that an institution like us were doing tests at a cheaper price than the private sector, okay? So obviously you create some kind of movements and these would have some type of problems. Also, in the type of missions that we are thinking, okay, would have a huge logistic problems. They are missions because they are difficult to implement. So it's not that we are much better than the other ones and nobody thought about it. They were already there, correct? But nobody was able until now to find solutions that are easy to reach a lot of people. That massification sometimes is easy to find the prototype. The problem is, how are you going to massify these and really the thing here, what we want to reach is the highest number of people possible, okay? Ideally everyone that is in it. And so obviously I think that is going to be a lot of problems there.
Okay, so essentially internal and external factors at the end of the day. Thank you so much for the clarification.
Who else had questions?
Mm-hmm.
Okay. I should never have said that we had plenty of time, because we don't anymore. But I'm gonna allow another 2 questions, 3 maximum.
Kind of
okay.
Mm-hmm.
Hello, thank you for your talk. It was very interesting. I know IMM for quite a long time, but I was wondering if you have already thought or being implementing some strategy to fight antimicrobial resistance, because some scientists, say that it would be maybe the next big pandemic. And I was wondering if you are thinking or doing something related to that. Thanks.
No, we are not, okay? And in fact, there was a startup company that was initiated at IMM a long time ago, Technophage. That concept was that it was phages, to combat antibiotic resistance, but they are not part of in fact, they sit at IMM, part of them and everything, but they are not part of IMM itself. But you are totally right. That should be really
that
something
should be your next mission, or IMM Care's first mission.
Yeah, but that is not really a mission for IMM Care. IMM Care wants something that is already in place. You need to have some research development, obviously, for IMM Care missions. It's not just to repeat what others are doing, but needs to be something that is close. But it would be really beautiful to have a research line, because it's another thing. Is one thing that I didn't mention here, because only started to be in our minds for the last 2-3 weeks, is that we need really to have clinical research lines that are not just are driven by discovery, but not really curiosity itself, but a research line that is really fixed on this type of focus. And I agree with you that this is really an important one.
Okay, José Pedro, tinhas...
Maria, just a comment, just a small thing. At Karolinska Institute, they have been building up also a biobank based on the very well organized health system in Sweden, but they took a lot of advice from the Icelandic experience. I don't know if you thought about it. You know, Iceland is completely organized, as everyone has a sample there. And
No,
they
the
are,
Nordic countries are always what we say that, you know, we need to go and talk to them and see exactly how we're going to do this. To be honest, we just finished to put together things on 8th of September for this proposal, okay? So now is when we are starting to break stone, and we need really to have, you know, we already had an advisor from, in fact, I'm not so sure if it was Sweden or Denmark, something like that, that was advising us already. Is a paragraph, so it's not much, okay? What we propose, making the proposal is not like a big part, but we really need to start to
but talk with the Icelandics. It's very impressive.
Okay, fine. Thank you very much for your advice.
One last question. Okay.
Thank you, Maria, for your very interesting presentation. You focused a lot on the innovation part and what scientists should be doing on that area. But what about the dialogue part? We know that scientists, as you mentioned, the dialogue part. We are facing some backlash, some very organized movements trying to spread misinformation or non-scientific information and threatening scientific discovery. And while in the United States, we have all those scientist pop stars that can manage to sell books and find sponsors and keep their like a job of promoting science here in a smaller country like Portugal. It would be less not so easy to do. Do you think research institutes also have a role to play on that? Certainly. Or should be a more broader approach to this?
I really think each research institute have a responsibility to do that. So part of the budget needs to be allocated to that. That doesn't mean that these people that are responsible for this would not organize at national level and they would become a single voice. Okay, one thing that is very important is that, and here is we have a kind of a different problem. Okay, and I think the first thing that they need to focus is to explain to the population why doubt is not fear and is not a problem. Because that is the problem, is that, you know, and we could see this during the pandemic. You have people like Miguel or, you know, at IMM, several of them were going to television and they not always would agree exactly what they would say, okay? And the problem is that when people listen at home, they think, oh, but why one thinks this way, and they are even from the same institution, okay? And that is one thing that they are free, because it's one thing that people need to understand, they are free, and this is just an opinion. One thing is facts, the other thing is with these facts you build an opinion, but it's very important because they are the majority of these people that then go into television in these situations, they almost are forced not to say, we don't know at the moment, because we don't know at the moment, next day is on social thing, is like saying, my God, if they don't know, we are going to be killed in whatever. No, they need to understand that for us, not knowing is what drives us to know next day. Okay, so there is a Nobel Prize of physics, how will you say, a guy that in physics, okay, that received a Nobel Prize in physics. I cannot remember now his name, but I have written somewhere that asked, so there was a saying in Germany in physics or whatever that is like, what we don't know now, we will know whatever, okay? And he asked when he died to be written in his
tombstone.
Exactly, we will know. And that is the thing, is that what I think is the main principle that we need to make people understand, that is no problem that we don't know. We will know. It takes time, obviously, but we will understand our world, and that is, you know, that understanding only comes because there are people that are curious and are going to understand. What is the problem is that to combat the so quick popular type of things, okay? And I hope I don't offend anyone here, okay? But when we talk these days that fake news are really something of the present, they are not present, okay? We really have religions, okay, that were made in a belief that we know that is not possible to happen, and people know, even people that are religious these days, correct? The majority of our country is Catholic, okay, and they believe that The baby was born from a virgin woman and really got back alive after dying. We know that this is not possible, and it's just a way of, even church understands that this is just a way of explaining life. Okay, I understand that, but it lasted for more than 2000 years. Okay, so really, it's really, and so is something that we need to understand. Is not what is different, it's the speed. The speed now, and it's very difficult to combat that speed, because as soon as it's all over there, everyone seems to believe certain things. So that is why I think we need to unite it in the country and internationally to make sure that people are not worried of things that we don't understand. I think that would be.
I just add the speed and the scope, because now the fake news reach many more people than they could before of the internet. Okay, this is really interesting and, as always, fascinating to discuss these subjects, but we really have to move on. And in fact, I think I'm going to suggest a change for logistical reasons, because we need to have the results of the competition before 1 p.m. sharp. I'm going to, if the three speakers don't mind, instead of having the 3 talks and then the students, we start with the students and then the 3 talks. Is that okay? We still finish at around the same time, but we have the pitch presentations by the students before David, José Pedro and Idalio give their talks. Is that okay with the 3 of you? Okay, so in that case, I ask the students that have their pitch presentations to come forward, and we start with Marta Narciso from IMM, and she will tell us about tissue tropism and parasite virulence in recently isolated Trypanosoma brucei strains. She's a master student at Instituto de Medicina Molecular in Luisa Figueiredo's lab, my neighbor, and welcome.
So, good morning, everyone. My name is Marta, and I work with Trypanosoma brucei, which causes sleeping sickness in humans and again in cattle. Inside the mammalian host, the parasite circulates in the bloodstream, and it's also able to invade tissues, being the skin, the adipose tissue, and pancreas, known as being a major extravascular reservoirs. In research, experimental infections have been done typically using the Antat 1913 clone, and this is now fully laboratory adapted. And in 2016, 2 new strains of Trypanosoma brucei were isolated from the field, MAC65 and MAC98, which are going to be the focus of my work. And my question is to understand how similar are these 2 new recently isolated strains comparing to the one that is used in the lab. So, starting with in vitro behavior, we placed parasites in culture, and we saw that they have different growth rates, and that MAC98 had a slower proliferation, where MAC65 is the fastest one to divide. Regarding in vivo studies, we infected Black 6 mice, and we saw that MAC strains gave hyperparasitemias, comparing to the wave pattern seen in Antat. They also lead to weight loss, although not as accentuated as Antat. And also MAC strains lead to acute disease, with MAC65 being more virulent than MAC98. Also, in further experiments, we also lowered the inoculum that we used and also tested different hosts. However, we did not see a change in MAC65 or MAC98 phenotype. Lastly, we saw tissue tropism to the organs, and we saw that MAC strains have tropism to major organs. However, in main known extravascular reservoirs, MAC98 seems to be more similar to the Antat strain. So, in conclusion, the strains in study exhibit different phenotypes, and for this, our study highlights the importance of using multiple strains when analyzing infection phenotypes, as pathology can be strain dependent. I would like to acknowledge my lab and all of you for listening. Thank you very much.
Thank you, Marta. I remind everyone that all these speeches that are being presented here also have posters downstairs, and you will be able to ask questions or discuss with the student their work during lunchtime. And so we move straight to Joana Rodrigues, please, who is going to tell us about, she's from Instituto Superior Técnico, and she's going to tell us about improving the worldwide vaccination plans for COVID-19, a comparison of alternative strategies. Welcome.
Hello, my name is Joanna. It is with great pleasure that I present to you this project. As you know, during the year of 2021, the COVID vaccines access has been extremely different across countries, and therefore we hypothesized that maybe alternative strategies of vaccination could have prevented a lot more deaths. Therefore, the objectives were to evaluate whether global-based strategies instead of national-based strategy would be a viable option, and to consider different prioritization strategies. Those being a demographic prioritization, age-based, an epidemiological prioritization, this is based on the cases, and a mixture of both. To do this, we had the methodologies with 5 key steps, starting by the extraction and cleaning of the input data, then a simulation of these alternative distributions. Then we estimated the alternative number of cases and deaths that would occur in each of the strategies using the population prevented fraction, and we conducted a sensitivity analysis and a comparison of the strategies. With that, we obtained the following results. We see that for the prevention of cases, the observed allocation of vaccine has been the one that has actually allowed to prevent more cases, but regarding deaths, this is not the case. A different alternative strategy could have prevented additionally 200,000 deaths, and that would be the epidemiological prioritization, which is based on the number of cases that each country has. Regarding the income group, we see that high-income countries are the ones with highest vaccination rates, but upper middle-income countries are actually the ones with the biggest death prevention because of the fragility of their healthcare systems. However, these results are extremely affected by countries using either zero COVID strategies, but principally because of countries with high proportions of underreporting, which may have underestimated extremely our results. As a conclusion, this study reinforces the importance of global coordinated action worldwide, and it also highlights the impact of considering novel prioritization factors, such as the number of cases, which has allowed to decrease mortality by 5.6%. And finally, it advances methods that can be applied to other settings and can also be applied not only globally, but within countries or regions. Thank you for your attention.
Thank you. So I would now like to call Sofia Lopes, also a master's student from Faculdade de Farmácia, who is going to tell us about formulation of a carrier system to deliver CRISPR-Cas-based antivirals. Thank you.
Hello, thank you. So today I am here to talk about the theme of my master thesis, which is the formulation of a carrier system to deliver a CRISPR-Cas-based antiviral. Sorry. And I would like to talk, and I would like to talk to you about the importance of finding a method to suitable combat viral infections quickly. And we have currently 2 options. We have vaccines and we have antivirals. And with vaccines, we had cases where it worked really well, as recently with the COVID infection, but others haven't led to long-term immunity. And with antivirals, the quickness of how virus mutates and the years it takes to develop and commercialize a whole new antiviral is a problem that plays against an actual application of quickly combating a new or recent virus. So my proposal is that we apply CRISPR-Cas systems in combating viral diseases, because once the system is formulated, we only have to change the the genetic sequence of the single guide RNA to attack a new genetic sequence, for example, when a new virus appears or there's a new mutation. So, and due to the lack of bioavailability, these systems need to be coated and need to be encapsulated. So my thesis work was to develop, formulate, characterize, and compare 3 types of nanoparticles capable of encapsulating the single guide RNA and the mRNA, the 2 molecules needed to activate the CRISPR-Cas system. So in partnership with the University of Munich, we were able to formulate 3 types of nanoparticles that demonstrated optimal characteristics for in vivo administration, set with an very efficient encapsulation efficiency, low levels of cytotoxicity, and allowing gene expression. And although further studies should be carried out, for example, to prove cellular uptake, the results were very promising and suggest that gene therapy might be applied in combating viral diseases in the future. Thank you.
Thank you very much. So we now move to the last of the master students, and that's Mónica Lopes from Faculdade de Ciências, and she will be talking about approaches to control the COVID-19 pandemic. Thank you.
So, hello, good morning, everyone. My name is Monica, and I'm here to briefly present my master thesis, which was based on two projects that focused on addressing critical questions regarding the new pandemic. So, in the first project that is now published in PLOS ONE, we have developed a high throughput neutralization assay suitable to use in BSL-2 settings for monitoring SARS-CoV-2 evolution and escape to immunity. So one of our main conclusions was that the beta and gamma variants, who was first detected in South Africa and Brazil, showed greater resistance to neutralizing by antibodies compared to alpha variant, which was first detected in UK. We also identified two amino acid residues in spike protein with potential to evolve immune escape mutants. So this project generated tools and knowledge important for close surveillance of viral strains and also informed development of vaccines and therapeutics. In the second project that is now published in PLOS ONE, we have established a 98% accurate saliva molecular testing in adults and asked whether the method was suitable for children up to 10 years old. And we managed to efficiently diagnose SARS-CoV-2 infected and uninfected children with our method, which involved RNA protocols with RNA and without RNA extraction. And for these contributions, for trying to simplify COVID-19 diagnosis in children, this project won last year the grand prize of the Portuguese Society of Pediatrics last year. Thank you.
Thank you. So we now move to the 4 presentations by PhD students, and the first one is Francisco Olivença from Faculdade de Farmácia, who will tell us about harnessing the full potential of beta-lactam application in tuberculosis therapy by exploiting genomic patterns of Mycobacterium tuberculosis susceptibility and synergy with conventional agents. So it already won the prize for the longest title in the competition. Thank you.
Good morning, my name is Francisco Olivença and I'm a PhD candidate at the Research Institute for Medicines. As we all know, antimicrobial resistance has emerged as one of the leading public health threats of the 21st century and could be responsible for up to 10 million deaths per year in 2050. Notably, drug-resistant tuberculosis accounts for about 1/3 of all deaths related with antimicrobial resistance and requires longer regimens with drugs that are more toxic and much more expensive. Excuse me. So in our project, the aim of my PhD thesis is to clarify 3 underexplored aspects of beta-lactam application in order to maximize the outcomes of this currently used antibiotic in tuberculosis. So far, our results have been published in 2 papers. In the first, we have shown that different Mycobacterium tuberculosis strains have variations in beta-lactam susceptibility, while in the second, we explored the resistance mechanisms to this class and discovered potential novel targets. Currently, I'm exploiting synergies with conventional anti-TB drugs and their role in pathogen evasion capacity. Collectively, our results show that proposing beta-lactams against specific strains and combining them with the antimicrobacterials could result in a maximum outcome of this class. In addition, our integrated perspective demonstrates the importance of taking full advantage of currently available antibiotics in the fight against antimicrobial resistance, especially when novel classes are not delivered. I invite you to visit my poster where I gladly answer any questions that you may have. Thank you so much for your attention.
Thank you. And now, also from Faculdade de Farmácia, we have Francisco Martim. Do we? Okay, so we're gonna jump Francisco Martim and go straight to Mónica Galocha from Instituto Superior Técnico. We'll talk about unveiling new pathways of genomic evolution towards azole resistance in Candida glabrata.
What am I doing? Okay. Okay. So, did you know that fungal infections affect over 1 billion people and are responsible for approximately 1.5 million deaths every year? And that Candida species are among the most common cause of these fungal infections? Well, that's right. Candida species are well known for causing superficial infections in the mouth, skin, nails, and reproductive tracts of both male and female. Unfortunately, 3 out of 4 women experience at least an episode of vaginal candidiasis in their lives. These kind of infections result in compromised life quality and high costs for the healthcare system. But more worrying, Candida is also a common cause of life-threatening bloodstream infections in hospitals associated with high mortality rates. Candida glabrata ranks as the second most common cause of severe Candida infections, supported by rapid acquisition to antifungal therapy to the most used antifungals, azoles, and echinocandins, frequently prompted by mutations in the resistance biomarkers PDR1 and FKS genes. However, several resistant isolates can acquire resistance through alternative yet unknown mechanisms. So, in a genome-wide association study perspective, we analyzed nearly 100 genomes of susceptible and resistant Candida glabrata isolates, and looking deeper into those with no alterations in the typical resistance biomarkers, we searched for alternative mechanisms underlying the resistant phenotype. Among other interesting findings, we unveiled the role of some components of the mediator complex and of exhaust transporters in Candida glabrata azoles resistance. The most exciting of our findings has just been published and states that azole molecules enter fungal cells through exhaust transporters, and we believe that this paradigm-changing discovery will help to understand why azole therapy fails or succeeds depending on the species or on the strain found in the clinical setting, while contributing to improve antifungal therapies. My name is Monica, and I'd be pleased to answer all of your questions and tell you more about it near my poster. Thank you.
Thank you. And so, last but not least, Isa Motinho from Faculdade de Medicina Veterinária, development of potent and broadly neutralizing antibody fragments for COVID-19 derived from domestic cats naturally infected with SARS-CoV-2.
So, good morning, everyone. My name is Isa, and I would like to present you my PhD project. So, as we know, SARS-CoV-2 and the resulting disease, COVID-19, are one of the greatest public health concerns worldwide. Although vaccines have been approved globally for emergency use, the rise of new variants of the virus makes the development of new strategies essential to control the current pandemic and prepare for future outbreaks. Monoclonal antibodies, in particular single-domain antibodies, are a promising approach, though to their small size and access to hidden epitopes. Our strategy is to develop a single-domain antibody that can block the interaction between the virus and the target cell. But what is the origin of these antibodies? These antibodies are derived from cats naturally infected with SARS-CoV-2. According to our results, cats develop potent antibodies capable to neutralizing alpha, delta, and Omicron variants. In our approach, we intend to develop a cat-derived single-domain antibody that can be used in human medicine, but also in veterinary medicine. For more details, I invite you to visit my poster, and I will answer your questions. Thank you.
Thank you. Last call for Francisco Martim, who wasn't here before. He's still not here. So with this, we finish the presentations from the students. I would like to remind everyone that these presentations are accompanied by a poster. And I think we have seen very good teasers for nice work that we can discuss in more detail if we go during the lunch session to see the posters. And now we move straight to the 3 presentations that were scheduled actually for before the students' presentations. We've changed the order, but we are now ready to move forward with these presentations as soon as my computer turns on, which it doesn't want to do. Diz? Não, deixa estar, tá, ok, obrigado. Okay, so we start with David Pires, and David is an assistant professor of immunology at the Faculty of Pharmacy of the University of Lisbon. He's also an assistant researcher at the Católica Medical School of the Catholic University, and he will be giving us the results of his research on the proteolytic pursuit for a host-directed therapy for tuberculosis. Thank you.
Thank you so much, Miguel. And I'm very glad to be here today presenting some of my work, as I'm sharing this room with 2 professors that were very inspirational for me during my college degree of microbiology, Maria and Miguel. So I'm very glad to be here. I'm going to present some of the work that I did mostly at the Research Institute for Medicines of the Faculty of Pharmacy, our proteolytic pursuit for host-directed therapy for tuberculosis. So I'm mostly a product made in the University of Lisbon. I did most of my formation here, so you're partially to blame for whatever it comes out of my scientific career. And during my stay at the University of Lisbon, I became very interested in this very old disease, a great burden for humanity, that is tuberculosis, especially when we started developing more urban societies. And this disease is so old and it's so interesting that we can even track the migrations of the human species around the world by tracking the lineages of Mycobacterium tuberculosis, the pathogen that causes this disease. We can trace this from the out of Africa migrations of humans, and even the expansion, trade, the conquest, the many stories of humanity. Tuberculosis has followed humans wherever we went. And this disease is so old that even for Hippocrates, when he described some of the aspects of the disease, this was already an old disease. And it was already an old disease for the mummy, where we found DNA of these vestiges of Mycobacterium tuberculosis. And what is this disease? So tuberculosis is an airborne disease caused by a pathogen, Mycobacterium tuberculosis. It's spread from person to person through liquid droplets. These droplets lead to the deposit of this bacteria in the deep tissues of the lung, where it encounters innate immune cells such as macrophages and dendritic cells that elicit, the entire immune response, migration of T cells to the infection locus, and to the formation of the hallmark structure of tuberculosis, that is the granuloma. In the majority of cases, this leads to contained infection, the latency state. But in some cases, it leads to disease and the production of lesions mostly in the lung. There's a treatment for tuberculosis, a cocktail of 4 different antibiotics, and that's mostly one of the reasons why we are able to have this session indoors today, or otherwise, as you can see in these pictures from the beginning of the 20th century, we would have to be staying outside like these children would do to avoid the transmission of tuberculosis, as one of the many measures that society was implementing to try to cope with this disease. We were on a slow but on good track to control tuberculosis until now, but with the onset of the COVID-19 pandemic, we had a huge reversal on the progress that was made. Tuberculosis is a very widespread disease, more than 10 million cases every year, and it's the 13th leading cause of death. As I told you, it's a treatable disease, and many lives, millions of lives have been saved from 2000s until today. But of course, the great problem, as it is with most infectious diseases, is the rise and evolution of drug-resistant strains. And these drug-resistant strains force us to use second-line, more toxic and expensive antibiotics that increase the length of treatment for up to 20 months, which is quite impressive, and the reduction on the success rate of these treatment to about 60%. And fortunately, new molecules started to appear in the last few years. For more than 14 years, there were no new antibiotics being produced against this disease. But as always, this is a never-ending story. When we produce new molecules, these molecules are implemented in the clinic, and of course, new drug-resistant strains start to evolve and put the process back to the beginning. Also, vaccine candidates, although there are some promising ones, we haven't had much luck until today. So what the structure that we have been following mostly is try to circumvent this problem, targeting the host instead of the pathogen, and targeting the host immune system, trying to prevent the evolution of these drug-resistant strains, trying to produce some type of solution that can be used in synergy with the conventional therapy, and especially trying to overcome the mechanisms that the bacteria uses to hinder the processes of to impact the processes of our immune system. And why is this important? So we would expect in a normal case of infection, macrophages would engulf the bacteria, and then through the release of several detrimental effects against antimicrobial effects against the bacteria, we lead to its destruction. But what happens with Mycobacterium tuberculosis is this bacteria is able to avoid or resist some of these mechanisms and finds in the very cells that should destroy it the niche where it replicates. And in this niche, it will find a much more easy environment for it to replicate and survive, with lower proteolysis, lower lipolysis, and a mild pH that is not so detrimental for the bacteria. And among all these aspects, one that we found was very unexplored, and we decided to look more into it was the proteolytic process in these cells. So if we want to look at proteolysis inside macrophages, we need to look at catepsins. They are the major group of proteolytic enzymes in the lysosomal pathways. They are synthesized as inactive proenzymes. They are adapted to the medium of the acidic medium of the lysosome, and they perform roles related to cell homeostasis in very different roles, like protein processing, cell death, inflammation, pathogen killing, antigen presentation, etc. So what we would expect from the action of these catepsins is, like I told you, the destruction of the pathogen, the processing of its antigens, and then also, as some catepsins like catepsin S would do, is the processing of the antigen presentation machinery, like class 2 HLA molecules, that would allow the stimulation of T lymphocytes. But when we looked into macrophages infected, human macrophages infected with this bacteria, what we saw was a very pronounced pattern of downregulation of these catepsins. So these catepsins were not being produced in response to this infection, unlike what was happening when we infected macrophages with a non-pathogenic bacteria. And what were the consequences, we asked, about this manipulation, about this downregulation? So when we selectively silenced several catepsins during infection, we could see there was a great improvement in the survivability of the bacteria. So these catepsins were clearly had a role in the containment and the control of the survival of these bacteria. Moreover, as I told you, these catepsins can also be important for antigen presentation. And when we checked the surface expression of type 2 HLA molecules in catepsin S silenced cells, we could see there is a marked reduction in this, as is well known, and we confirmed this during infection. So having this downregulation of catepsins during MTB infection would clearly benefit the bacteria. So normally we have found the problem, so we need to find some solution, some intermediate, some explanation for what's happening that we can target. And using bioinformatic tools, we found a curious and interesting microRNA that was a potential regulator for one of these key catepsins, like catepsin S. And when we searched for the expression of this microRNA during infection with the MTB, we saw that the expression of this microRNA would increase early on during infection, while the cathepsin S protein levels would decrease. So these were already hinting us that this could be a regulator for cathepsin S. And when we use the luciferase vector, we could demonstrate that the microRNA would target the 3' UTR region of the messenger RNA of cathepsin S, and thus demonstrate there was an interaction. This microRNA was inhibiting the expression of cathepsin S. So if in the normal scenario that we were exploring, we would see high levels of this microRNA and low levels in consequence of this cathepsin S that were hindering bacterial destruction and antigen presentation. Our solution would be to use a microRNA inhibitor. That's what we did. And using this solution, we could restore or even improve the levels of cathepsin S expression, increase the ability of the macrophage, a slight increase, but still relevant increase ability of the macrophages to destroy the bacteria intercellularly, and also the ability of these cells to express HLA type 2 molecules at their surface and prime T lymphocytes with MTB antigens. Now, okay, we found an interesting regulator intermediate to restore cathepsin expression, but we also asked, okay, can we act at different levels of this problem? Could we perhaps improve cathepsin activity? And we asked this question because we already knew from our studies that cathepsin activity was not only its expression is lowered, but even the activity of the expressed cathepsins is also lowered in infected macrophages. So we looked at the regulation pathways that lead to the regulation of cathepsin activity, and we found one interesting possibility, that these endogenous regulators that are produced by our very own cells to regulate cathepsin activity. And among these, one specifically, cystatin C, is one of the most potent inhibitors of cathepsin activity. So we thought, let's try just see how important this cystatin is. And we treated infected macrophages with this cystatin, just added the protein. And we saw a huge increase in the survivability of the bacteria. So this cystatin clearly could have a great impact during infection. So, okay, we had our endogenous regulator that we could perhaps use as a target. But could we find an exogenous regulator? And by that time, we found a very interesting paper that was saying that protease inhibitors used to treat HIV would impact the activity of human cathepsins. And particularly one, saquinavir, could even increase the activity of these human cathepsins. So, okay, we have our exogenous regulator. So let's test this out. And by testing the silencing of cystatin C or the application of saquinavir in MTB-infected cells, we could see first a marked increase of proteolytic activity in these infected cells, so countering those effects done by the bacteria, resulting in a very significant reduction of the survivability of the bacteria. So the intercellular killing of MTB in macrophages was being increased with these two treatments. Their capacity, once again, of these macrophages then to express at their surface antigen presentation molecules, HLA type 2. And finally, the ability of these cells to prime T cell response and induce their proliferation in response to the presentation of MTB antigens. So for each one of these problems, we tried to find the different solutions. These were published solutions. And now the next steps that we are envisioning, and we are already at the final stages of one of them, is try to put these solutions in a drug delivery system that can then be administered to more complex models, animal models, and so on. So this could not be done without the help of all these amazing colleagues, mostly the colleagues at the Research Institute for Medicines at Elsa Ange Lab, and all our great collaborators around the world. So thank you all for your attention.
Thank you, David. So thank you also for sticking to time. That's very appreciated. And are there any questions? Yes.
A nice presentation, thank you. I just want to know if there is a metabolic model for the bacteria that provokes tuberculosis, like in for instance, for Candida, you have metabolic models in which you can like predict if you delete a gene or a set of genes, you would have like less biomass, or the strain would not be viable. Like I think it's an interesting strategy to start like to test some different approaches and then pass, of course, to laboratory to test the hypothesis that you tested first. I don't know if there is, I'm just asking.
Metabolics of tuberculosis is kind of a hot topic now, so people are investing it right now. So your question is right on time, but yeah, we still have lots to answer about that. But there are very interesting papers coming, so it's one of the things where researchers are investing right now. So I believe there will be very interesting models coming up in the future.
Well, really cool stuff, in my opinion. Have you thought about making any kind of experiments of synergy, like isobolograms between saquinavir and the classic dot kind of cocktail?
Yeah, that's one of the things that we would like to explore. Right now, the next step that we thought was logic is, since lots of the things that I showed you, they are easy to do in the lab, but translating them to a clinical approach would be the difficult part. So now we are investing more in trying to develop a way to deliver these solutions to cells, to animal models, etc. But then, of course, our main objective would be to use this in synergy with the main therapy, as although we have a great bet on these host-directed therapies, we are perfectly sure that antibiotic therapy is still the greatest weapon that we have, and our solution is try to improve that antibiotic therapy. So of course, our idea is in the future to have a combination and try to test this synergy. Yes, not right now, but of course.
Any more questions? If not, I think we are right on time. And so thank you very much, David, once again. And now we move to the second talk by José Pedro Gil. José Pedro is principal investigator and associate professor at Karolinska Institute, and he works on malaria, on Plasmodium falciparum, and in vivo and in vitro response to artemisinin combination therapies. And he will talk today about artemether lumefantrine decreased efficacy is associated with PFM-DR1 gene duplications in Africa. Thanks a lot, Pedro.
Thank you. Good morning. I think you listened to me. So, after a lot of in vitro, we're going to travel a little bit to Africa, because our part of the work of my group in Sweden happens actually in the field with clinical trials. And I'd like to start by this drug. It's a wonderful drug. It's called, originally from Novartis, called Coartem. It's a mix of artemether and lumefantrine. It's a fantastic drug. It's an antimalarial. It's the most used antimalarial in the planet for the management of uncomplicated malaria. Has been administered for at least 5 billion times since its introduction about 15 years ago. It's cheap. It's very effective, 99% efficacy. It has a shelf life of at least 2 years. Nowadays, is out of the royalties, is very inexpensive. It's a great drug, and it's the backbone of the malaria control programs all over Africa. It's the first line in most of the programs. But something started happening. This is in the north of Angola. This is the Zaire area, just bordering the RDC. And CDC has been helping the National Malaria Control Program in Angola for a long time, making the old mandatory every 2-year tests of efficacy, in vivo efficacy trials as such, of antimalarials. And then last year, something is going on there. In the very north, the efficacies have been gone a little bit apparently below the obligatory 90% efficacy, corrected efficacy by WHO. This has stirred a lot of controversy. Is it really resistance rising or not? Well, usually Coartem has a 99% efficacy. As I said, it's a beautiful drug when it's really like administered with all supervision. The problem with these several trials was always the same. Coartem, or artemether-lumefantrine, AL, as from now on, has 6 doses. 3 of them are during the night. When you make a clinical trial in the community in the middle of Africa, it's not easy to go 3 in the morning to some village. You just don't control that part of the trial. So you don't control half of the treatment. Now, antimalarials, they work fast. After, say, 24 hours, a kid that looks that he's going to die and can die is actually quite okay in the bed. It's quite many times already playing and all that. So we know that we shouldn't stop the treatment, but communities are communities, and very poor communities are very poor communities, and they see the kid already, almost good, and they stop the treatment many times, or at least they don't take the ones in the night. So there was the need of a trial, an hospital-based trial, where the kids would be supervised on all the doses of the treatment, and this has never been done in the area. So we did it. We calculated 100 patients would be enough. And this is a open label efficacy trial. So no comparison arm in this case. The children were recruited in one place that I'm going to talk a little bit about. They stayed 3-4 days inside the hospital. They were isolated completely from any kind of reinfection from mosquitoes, whatever, and all the treatment was made absolutely ideal in accordance with all the parameters. Then we liberate them, and there was a follow-up of 42 days to check if the disease would come back somehow. This is a place, it's about 75 kilometers north of Luanda. It's, even though it's not very far from the city, is a very, very poor place, even though the health center was quite nice. That's the reason it was chosen. Anyway, we improved the conditions. We created a new ward for the kids, including toys, a very important tool for maintaining small kids used to be playing outside for 3 days inside one relatively small room. We had a long training of the team. In fact, I even put myself explaining pharmacokinetics to the field team for them to understand why they had to be patient for 42 days to try to find the patients back to the clinic. The team just before, we were all very nervous, as is usually in the beginning of the clinical trial, and then starts the point. So we recruit, we check, classical slide. If it's positive, which was, here is the lab in the field, then the blood spot is taken and the kid is hospitalized, and I don't have photos of the hospitalization for ethical reasons, and followed up in the area for 42 days. I can tell this is it seems not a big deal and not very technological, but these kind of studies in the middle of Africa are a serious undertaking to be done properly. So what happens? So we were successful. It took exactly 1 year to have 100 patients with full follow-up. We had actually 4 drop-offs, which is quite good. And among the 96 remaining, we had 22 recurrent infections. And from those, 16 were reinfections, new infections, and 6, according to molecular analysis made a posteriori, they look like recrudescences, meaning the same parasite as in the beginning. So candidates of resistance. That gives us a 42-day follow-up, 94% efficacy. Well, it's a decent efficacy, but it's not the 99% that we usually see with artemether-lumefantrine. So maybe something was going on there. And thinking about it, we checked one gene. PFMDR1 is a gene that codes for a transporter of drugs, an ABC transporter that locates in a lysosome, a special lysosome in the Plasmodium parasite called the food vacuole, where the parasite actually processes hemoglobin. And this protein is oriented towards the lysosome. So what happens is that the parasite, for some drugs, and especially for a drug called mefloquine, it uses the food vacuole kind of a bin. It just transports the drug inside the food vacuole in order to avoid its action, which is mainly outside the food vacuole in other parts of the parasite. This has been seen very clearly with mefloquine. Now, mefloquine is a drug that structurally is similar to lumefantrine, one of the components of this combination we were testing. Resistance to mefloquine, which is very well known in Southeast Asia, is based on duplications of this gene. The parasite just makes more of this transport to kicks more of the drug inside the bean. And this has almost not been seen in Africa for many years. But now when we checked it out, it was there, and it was there big time. In fact, it was there apparently as duplicated copies in 12% of the infections. But more importantly, when we compare the frequency in the beginning, before the treatment, with the frequency of this mutation among the recurrent infections, there's an enormous increase, 12% to 42%, a very strong signal that the parasite is, like in Southeast Asia, using this mutation, this protein, bigger quantities of this protein to evade the drug action. Concerning the 6 recrudescences, so the 6 resistant candidates, let's call it like that, this is a slim data because it's a relatively small clinical trial, but we saw something weird, not weird, actually almost expected. Among the ones in the beginning that had duplications, 3 of them, they became recrudescent, while the other 3, it was among the parasites in the beginning didn't have. So this gives an odds ratio of 2.5. Large brackets is true, but definitely significant that having this mutation in the beginning is a bad idea, or a good idea for the parasite. It is actually, as we see it, a marker of resistance to lumefantrine as it is of mefloquine in Southeast Asia. But another thing that disturbed us a little bit is when we checked what was the real prevalence of this mutation in the baseline. And, you know, infections in Africa, they are very mixed. They include several strains of parasites in the same patient. So you might have one which has duplications in a mix of a lot of them with single, and directly might not be very visible that duplications are there. But if you consider like 1.3-fold as like a threshold to be sure that at least there's some duplications in the infections, we realize that over 70% of the baseline of the infections already carry this mutation. The mutation is everywhere there. Probably has been selected for years, for about 10, 12 years by lumefantrine, by this treatment. This means one thing. The parasite is becoming lumefantrine resistance ready, but it's still a combination. We still have artemether. Now, when we talk about artemether, it's part of the artemisinin group of drugs. Resistance to it is based on another gene called K13. K13 is a gene involved in the digestion of hemoglobin. And essentially, when the parasite has mutations there, it slows down a little bit the metabolism. And as the artemisinin has a very fast, very short half-life, action, the parasite just slows down its metabolism to escape a bit the action of the drug. But it works. It works just too well. And what happens? We go back to Southeast Asia. In Southeast Asia, what have been seen is that the parasite first gained mutations in the PFMDR1. He gained these duplications. And the efficacy of in that place, artesunate mefloquine went down to 93%. This is a bit the situation we have now there in Angola. The parasite got mutations, got the duplications, and got now 93, 94% of efficacy. Still clinically relevant, but the parasite is really giving a signal. Now in Southeast Asia, if you see there, when he gains the second set of mutations, the K13 mutations, the thing just collapses. It just goes below 60% efficacy, meaning in each 10 treatments, 4 just fail. And this was the reason for a big crisis in Southeast Asia that, well, still is a little bit there. But in Southeast Asia has, well, say 1.5% of the global malaria burden, while in Africa is over 90. So something happening in Africa like this, the collapse like this of a drug, which is the backbone of the national malaria programs, is really something to be concerned. We didn't find mutations in K13. That's great. And that's why we still have 94%, but the parasite is waiting. Now, while we were doing this trial, in Uganda and Rwanda in Central Africa, K13 mutations start to appear. They started in Uganda, they expanded now to Rwanda. There are new ones in Ghana. It's a question of time until these mutations will reach Angola. Difference between Angola and the other ones do not have this PFMDR1 duplication. So in Angola, it's just one step from a big problem. It's just a question of K13 arriving and joining PFMDR1 duplications for the parasite to handle artemether-lumefantrine readily. So it's all bad news. Yes, it is. This is not actually good news, but at least we have given one thing. And here we go to translation medicine that Maria was talking about. We have a molecular marker for the countries to check and to do something that I think is the future in public health control, which is precision public health, which means that in countries, especially of large dimensions like Angola, with provinces which are at least the size of Portugal, this mutation can be monitored, and one prevalence can be considered as an alarm point, as a threshold where the drug artemether-lumefantrine should be changed for something else, at least for that region that has this mutation. Now, the silver line on this, and this comes from actually from our very old research at Karolinska, is that we know that resistance to lumefantrine and mefloquine is associated with increased sensitivity to another drug called amodiaquine. So in piperacin, that means that you have what is called a collateral sensitivity situation. If the parasite gains resistance to this drug, it necessarily seems to get sensitive to the other one. So this can be balanced as long as you have molecular epidemiological tools to warn you when you should change. And that at least we can give. It's not only bad news, it's bad news and the tool. And acknowledgements, well, I'd like to thank our team in Angola from CISA, which was absolutely incredible in very difficult conditions. All this trial was done during the COVID-19 pandemic. At the time, there were no vaccine, no drugs, no nothing. It was tough to be there. And at Karolinska, in my group that made the molecular analysis, of course, our funding from the Aga Khan Foundation, the Gulbenkian Foundation, FCT, Vietinska Prodet, and IKEA, that gave us a lot of choice. And this was really important for convincing the kids. Thank you very much.
Thank you. Thank you very much. Very interesting, very close to home as well. So I would like to ask if anyone has questions. Maria has questions.
Very nice, and it's nice to see the progress of it's happening. So do you think so? Because you see this duplication of these, and of course, resistance in other parts of the world is due to mutations in another molecule. So is going to be this different? How is this particular to here, or is it all over? How you see this happening?
I think that for artemether-lumefantrine, this is really the trend. Will be the same, and I heard last week in the HTMH Congress that a similar path is happening, for example, in the north of Burma or Myanmar. So this is actually seems to be the program that the parasite has to escape these kind of combinations.
Other questions? Margarita.
Thank you. Very nice, and a big step from the lab into these trials. So my question is, since you discovered this mutation on this ABC transporter, is anyone considering developing inhibitors because these transporters are not so difficult to inhibit, something that blocks the pore or?
Well, actually, we do not know how these antimalarials themselves, they work. But one hypothesis is that they actually work, some of them, by blocking a little bit the transporter. And I'm saying this because these duplications are actually effective if they are built up over a couple of SNPs that are already there and they are fixed. So it seems that the parasite first selects these SNPs and then duplicates the nice ones for it.
But I still have a question. So just to see if I understood, so in Angola, what you've seen is the MDR1 duplication prior to the K13 mutation. In Southeast Asia, it was the other way around, right? First MDR1, yes. No, it was not the other way around. It was this order as well, MDR1 and then K13 on top of that.
Yes.
But then you mentioned countries, I think you mentioned Ghana, was it? Where it was first K13 and now we're waiting for MDR1. Yeah. How do you explain that the order in which this is happening is different in different countries? Just random or?
Well, it's a question extremely difficult to answer because this usually has to do with the kind of transmission and the natural history of malaria of each country. But it's difficult to say. And for example, in Uganda, I know that there has been some, well, all over Africa, but in Uganda, unregulated use of artesunate alone that might have accelerated this effect.
Makes total sense. Yeah. Thank you very much once again. So we are running a little bit behind time, but not too bad. We now have Idalio. Idalio is recently a doctor. He defended his PhD recently after a few years in Luisa Figueiredo's lab at the Instituto de Medicina Molecular. And his work was very successful during his PhD. He published the main project of his PhD in Nature a few months ago. And I think he's going to tell us precisely about that work, which is entitled N6-methyladenosine stabilizes VSG transcripts. Thanks a lot, Idalio.
So good morning to all of you. It's a great pleasure to be here. So I'm Idalio Viegas, and I work in IMM in the Luisa Figueiredo's lab. I work with RNA modifications, and I will share to you a bit of what I did during my PhD. So I work with Trypanosoma brucei, that is a unicellular eukaryote parasite that causes sleeping sickness in humans and nagana in cattle. And because it's extracellular, the parasite is exposed directly to the immune system. The parasite proliferates in the blood and the tissues of the parasite. Therefore, the parasite evolved a mechanism to escape to the immune system that is called antigenic variation. And antigenic variation depends mainly on this protein, that is the variant surface glycoprotein. So this protein covers the entire surface of the parasite. So it makes a very dense coat. And the parasite, to escape to the immune system, needs two properties. One is monoallelic expression, meaning that the parasite has thousands of copies of the VSG on the genome, but only expressed one VSG at a time. So each parasite is covered by millions of copies of the same VSG gene. And the second property is the switching, meaning that the parasite can switch the VSG that has been expressed time to time, and that allows the parasite to escape to the immune system. How that works? So in the beginning of the infection, the tsetse fly bites you during the blood meal and you get infected with few parasites. That parasites start to proliferate in the bloodstream, leading to the colonization of the host. The immune system recognizes the parasites and start to attack the parasites and start to eliminate them. However, a few parasites in the middle of the population change the code, change the VSG, and that parasites can escape the immune system elimination. That few parasites start to proliferate again, start to increase the numbers of parasites, and that leads to the immune system fight back that new parasites, a parasite that has a new VSG code, and eliminate the population. However, meanwhile, some parasites switch already the VSG. Therefore, the parasite can make a chronic infection because they're all the time parasites with a different new code that can escape to the immune system. And that disease is lethal if it's not treated. So because of that, VSG is highly important. It's one of the most studied genes in Trypanosoma brucei. It is highly abundant. More or less 10% of all Trypanosoma brucei proteins are VSG. And this is because the mRNA is highly abundant, mainly because it's very, very stable. It's the most stable transcript on Trypanosoma brucei. When we think about post-transcriptional regulation and RNA stability, we think about microRNAs, RNA binding proteins, But more recently, RNA modifications are being studied as a post-transcriptional mRNA regulator. So if you look to the canonical nucleosides, RNA modifications consist simply on the presence of small chemical groups that are linked to the normal nucleosides. There are more than 100 RNA modifications described, very few in messenger RNAs, and N6-methyladenosine that is one of them. So we started to look for which RNA modifications are present in Trypanosoma brucei messenger RNAs. And after that, what are the functions of that modification on the messenger RNAs? Do they have a regulatory role or not? So to identify the RNA modifications that were present, we used liquid chromatography and mass spectrometry that allows us to measure the mass of the single nucleosides and see if there's any modification present. So this is the modifications that we found present in messenger RNA. Every time that you see a bar to the left means that was a modification that was depleted of messenger RNA, meaning that was a modification present mainly in ribosomal and transfer RNAs. However, the bar to the right, the blue ones, means that they are enriching messenger RNA, that are modifications that are in coding transcripts, RNAs that will code for proteins. And one that we found that is very enriched was M6A, N6-methyladenosine. So we focus our study on this modification. So if they are in messenger RNAs, they should be encoding transcripts. So our question was in which transcripts we can find M6A. To answer this question, use a classical pull-down and RNA sequencing approach in which you enrich for the modified transcripts with a specific antibody. So in this graph, you can see in red the ones that are enriching messenger RNA, and they are plotted against its expression, its normal expression. So we found more or less 400 genes that have transcripts with M6A. And what we notice is that a lot of the VSGs are enriched in M6A. We validated this observation by gene set enrichment analysis. And in the remaining of our study, we focus on the role of M6A on these VSG transcripts because they are very rich on M6A and because the importance for parasite virulence, as I told you before. So we decided to validate these results in RNA biochemistry approach. We use a method that is a combination of northern blot with western blot, where we can transfer the RNA to a membrane that was separated by size, and after we expose the membrane to anti-M6A antibody. So we did that in RNA samples from total RNA, that is all cellular RNA, including the messenger RNA, the ribosomal RNAs, and so on. And we separate after the messenger RNA fraction, that is the A+ fraction, that is mainly polyadenylated messenger RNA, and the A- negative fraction, that is ribosomal RNA and transfer RNAs. And we did that for the mammalian infective form and the form that is in the tsetse fly, that is the vector of this disease. As you can see, the signal is mainly in messenger RNA, meaning that this validates very well our mass spectrometry results. And we see a smear in both the bloodstream forms and the procyclic form, meaning that was messenger RNAs methylated. However, only in the bloodstream form, we see a very intense band that has more or less half of the M6A on Trypanosoma brucei, and that is the size of the VSG. And that validates our previous pull-down approach, showing that VSG was highly methylated. So after we want to map where M6A was in the VSG transcript, it is in the coding sequence, is in the 3' UTR, in the 5' UTR, where it was. So to address that, we designed a biochemistry experiment in which we design oligos, DNA oligos, to bind to the VSG transcript. And after we digest RNA with RNase H, that is an enzyme that only cleaves RNA-DNA hybrids. That way we have a site-specific cleavage. We can break the RNA where we want. So we design oligos that will cleave along the VSG transcript. And when we digest with that oligos, what we observed with oligo A and B, for example, was that the size of the intense band was getting smaller and smaller. So that validates that was VSG, the transcript, but was telling us that the M6A was located to the 3' end of the transcript. So the next oligos that we used was an oligo just in the end of the 3' UTR that will release the poly-A tail from the body of the transcript, and the oligo that will remove the poly-A tail, giving only the transcripts without poly-A tail. What we observe is that when we digest with oligo C that release the poly-A tail, the M6A signal appeared in the gel in the size of the poly-A tails. And when we remove the poly-A tail, the M6A signal completely disappeared. That was very interesting for us, and you get very interest because these results was telling us that M6A was located on the poly-A tail of mRNA, of the VSG mRNA, and that was the first time that one RNA modification was being detected on the poly-A-tail. The other RNA modifications were located internally in the body of the transcript. So we are very interested in this, and because the poly-A-tail is very important for the stability of the transcript, is the main pathway for mRNA degradation starts with adenylation, we start to look the dynamics of M6A in the poly-A-tail. So to do that, we block transcription to allow to follow what happens to the steady state mRNAs that are being processed and degraded. And during the time, we measure the levels of mRNA of VSG, the size of the poly-A-tail, and the levels of M6A. Remind that removal of the poly-A-tail is usually the first step in mRNA decay. So what we observe is that after we block transcription to follow the normal mRNA turnover, in the first hour, the M6A levels dropped exponentially. In more or less 1 hour at 60 minutes, we have more or less 20% of normal M6A levels. However, the levels of the messenger RNA in the poly-A-tail is normal. They did not change, meaning that M6A is being removed the poly-A-tail before the adenylation in mRNA decay. Only after the levels of M6A dropped more than 20%, we start to observe the adenylation in mRNA decay. That means that removal of M6A precedes the adenylation, and that observation leads us to propose the presence of M6A was making the adenylation more slower, was protecting the poly-A-tail from the adenylation. So another question that we had to answer is that VSG is highly enriched for M6A. Is M6A more or less half of M6A was located on the VSG transcript? So all VSGs are different to allow antigenic variation, but they are conserved on the 3' UTR. And was known the presence of this conserved motif on all expressed VSGs that are highly expressed. In this 16-mer motif was known for a long time that is important for high expression of the VSG. Its absence leads to very low expressed VSGs. So we ask if this motif can be important for high levels of M6A in the poly-A-tail of VSG. So we analyzed our RNA pull-down data, and we compared the VSGs that we detect in our samples. In yellow, you see the VSGs that are being transcribed but do not have the 16-mer. And in blue, you see the ones that are being transcribed but do have the 16-mer. And we found a very nice correlation between the presence of the 16-mer and the increased enrichment on the M6A pull-down experiment. So this led us to conclude that the 16-mer motif is helping the VSG to be highly methylated. We validated this in the RNA biochemistry approach using expressing ectopic VSGs with and without the motif. And we decided to look for the action of the enzyme that remove the poly-A-tail. So if M6A is protecting the poly-A-tail, means that the poly-A-tail, the adenylation machinery should be more active on the poly-A-tail that do not have M6A. So we use our mutants that we generate without a 16-mer motif that leads to less M6A in the poly-A-tail, and use a cell line where we deplete CAF1. CAF1 is the main adenylase in Trypanosoma brucei, and acts on the cytoplasm to remove the poly-A-tail and allows the transcripts to be degraded. Because of that, we measure the action of the CAF1 with using a method that allows us to measure VSG on the cytoplasm and in the nucleus, that is RNA fish. So if we look here, this is the levels of the VSG that has a wild-type 16-mer motif, and in green you see the cytoplasmatic levels, and in white the nuclear levels. And when we add tetracycline, we lead to the depletion of CAF1. As you can see, if we deplete CAF1, the wild-type VSG that has the 16-mer motif that is highly methylated is slightly affected. Now, if we compare this with the VSG that do not have the 16-mer, the first thing that you notice is that the VSG is much low expressed. It's missing something that allows the VSG to be highly stable. So, and when we remove the CAF1, we see a cytoplasmatic recovery, a partial recovery of the mutant VSG mRNA. And that tells us that the CAF1 acts more on the non-methylated poly-A-tail than on the methylated poly-A-tail. So briefly, what we show was that M6A is enriched in VSG mRNA, is more or less half of the M6A is in this very important transcript, and is located in the poly-A-tail. Was the first time that someone found RNA modification on the poly-A-tail. We show that the M6A is removed before the adenylation happens, in that we only have delamination in the cells when M6A was previously removed. A conserved 16-mer motif is important for high levels of M6A on the poly-A tail. And with this, we have this working model, the current model, where if we have a transcript, a VSG transcript that has this 16-mer motif in the 3' UTR, that leads to increased levels of M6A in the poly-A tail, and that is making the denylation slower and allows the transcript to be more stable. So, and this working model is being developed in the lab. There is new people that is starting on this model. They are answering additional questions that we are not able to answer now, because it was the first time we started this project on the lab, meaning what are the enzymes that add the methyl groups, the ones that remove the methyl groups, how M6A interferes with the denylation, is a direct interference, is recruiting some proteins to do, so that all of the questions that we are trying to answer. And to finish, I would like to all of the people, I was very fortunate to have worked with colleagues over the year. So this was a real team work, and everything was only possible because I was meeting a lot of people that helped me, teach me. We had a very good neighbors. We have a very day-to-day collaboration with the Prudencius lab and Maria's Motta's lab, and I met a lot of people that helped me. So that was very important. So thank you very much.
Thank you very much, Hidalgo. Fantastic. We are obviously past our deadline for lunch, but we still have time for 1 or 2 questions. Margarida.
Thank you. This was fascinating. I was actually wondering whether Brucey, I think Kruse adds the poly-A tail by transsplicing. I wonder whether Brucey also adds the poly-A tail also by transsplicing, and whether this unusual methylation of the poly-A tail has anything to do with this process.
So what in Trypanosoma brucei we have from transsplicing is a 5' spliced leader that is already with a cap, and the poly-A tail is added by normal polydenylation. So we know using microscopy that M6A is added in the nucleus before being transported to the cytoplasm. We don't know if it's co-transcriptional or not. So now we are looking for the classical methyltransferases that we don't know anyone that is conserved in trypanosome. So we are looking by de novo. But other possibility, that is a second hypothesis that we have, is that the cells are adding M6A through polyadenylation from pre-methylated ATP. So that's the second hypothesis that we are following, but we have no data to answer your question.
Specific methylate.
So we
specific poly-A.
So we described the canonical poly-A polymerase in trypanosomes. We have a second poly-A polymerase that no one found activity so far. So we are speculating maybe that second one could be doing this job. But what happens is that there are other proteins that has a domain like a poly-A polymerization that people think that will be important for adding, let's say, cytidines for the poly-A tail and uracils. That is now another field. But we have no data yet to test that, to show that that answer.
Thank you. Any other questions? So Maria was talking about how this discovery could go well beyond Trypanosoma brucei, and she even mentioned cancer as a possibility. So how do you see that possible link happening, and what's your views about the overarching implications of your findings? I mean, speculating, of course, but what do you think could be the future there?
So I think I can answer that in 2 ways. The first one is the novel biological features that we can find in other cells. For instance, if no one now found M6A in the poly-A tails of other organisms, but the truth is that the classical ways to look for M6A was focused on the internal M6A. People are doing pull downs and sequencings, and that loses the poly-A tail information. So now we know that there are people looking for M6A in the poly-A tail of other organisms, in human cells, in mouse cells, and let's say we have a collaborator that is trying to develop methodologies to do that, because it's quite challenging. And we are lucky because we have VSG that is highly expressed and allows us to do this biochemistry. But if MCCA is present on the poly-A-tail of few genes in human cells, that will be missed. So our collaborator is trying to develop a nanopore sequencing technology to allow to do that. It's not working yet, but we hope soon we will work. We have one PhD student in the lab that is collaborating with that project, so we wait for that result. The second one is that if we can add modifications to the poly-A-tail of transcripts with therapeutic intentions, and if that can lead to increased expression of that genes that we want to express in human cells, maybe that will help to improve, let's say, mRNA vaccines for COVID or for other disease. And that is one of the projects that we are working now. If we can improve the expression of other messenger RNAs with therapeutic applications using poly-A-tail modifications.
Would it be increasing the expression or the stability, or both?
We hope both. We hope both. What can happen sometimes is that we can try to add something, M6A. It will depend on the amount of M6A in the poly-A-tail that could interfere with the denylation, makes a more stable transcript. However, if it is too much M6A and start to interfere with the poly-A binding protein, so one can reduce the translation. So we are making that experiment so far, trying to see if we have that working.
Thank you. Thank you very much. So if there's no other questions, I think we close the session now, 15 minutes late, I'm sorry. Don't forget we have the roundtables this afternoon. I hope to see you there. We're gonna, in our roundtable, we're gonna discuss the future of biomedical research in Portugal. We have a panel of experts in this field that will be joining this roundtable discussion, including Maria Mota. And so I hope to see you there. Don't forget to look at the posters as well. We had already the presentations of all the students that have a poster downstairs, and we can take this opportunity now to look more closely at their work and ask questions. And I guess this is it for this morning. Thank you again for being here. Thank you to the speakers for their excellent talks. Thank you to the students for their pitches, and enjoy lunch. Thank you.